How was it? Hard. So, yes?
I have a question. How do you find the position, on one of the questions, you find the position of the highs and the lowest values?
So there is these programs that are, so the question is, how do I find the lowest or highest value? So I'll step back and first answer in general. So when I have any data, okay, I have to basically find a way to go through the data, okay, and look at these numbers. What you were plotting, you know, there were 3D contour plots or whatever, there was the cross-section or sense of, but those are just numbers. Numbers you were looking at were actually CT numbers, which correlate with the density of the material. So where you have void, you have close to zero density, and where you don't, you have sand, which has different density, and that's the differential you see in those grayscale values. Okay? But they're ultimately behind that, they're just numbers, and you're looking for minimum, maximum range, so you can analyze them. Okay? So normally, there's an algorithm that basically walks through your entire array, and for that you need to know the shape of the array, and basically just compares to what, as it goes, it compares and figures out what the smallest or the largest number is. We're going to actually work on that algorithm in the next lecture, when we need a for loop for that. So most of the functions that exist, there's that argmin, argmax, and there's at least probably 10 implementations of minimum, maximum function. They actually could return the location as well. So you go online and look up that function and see whether it can actually return the location. So you can search yourself, which is what we're going to learn actually how to do, and then find that location. But you could also, if it's a pre-programmed function, it has probably a way to return the information to you. Now, normally when a function is actually returning a result, okay, the way you possibly use it is to just kind of use the function and then you see a result printed. If you wanted to grab that value, you say maximum value equals to, right? And then you get that value. But probably it has an option for a couple of more outputs, which would give you a location. Okay? Does that answer everything? All right. So I just wanted to actually show you and comment on a couple of things. So this is actually the data set online. It's injection of nanoparticles, silver nanoparticles in this case, into sand. Now we inject nanoparticles in subsurface engineering for various enhanced oil recovery or remediation purposes. I'm not going to go into the details, but they're used, and this data set was actually doing a bunch of experiments and doing imaging of them with X-ray CT to see where those nanoparticles are. Now, you just looked at the sand part of it. It's one of the data sets there. But I just wanted to point out some visualization issues. So here, this is actually, you looked at the subset of one of these images. This is a cross-section of X-ray. You will see that this is just a grayscale, so this is the matter of how I want to color these images. It doesn't really matter. But the original data set was 350 by 350 by 45. We couldn't go above something that was 35 by 35 by 45 because even with that set, you had various hiccups with your programs. Sometimes it was waiting for the process, to read it, to process it, right? So there is actually processing time involved with three-dimensional data sets. So really this homework, if it was painful a little here and there, I just wanted to expose you to three-dimensional data. It's very common in reservoir simulation and engineering. 35 by 35 by 45, really in terms of size, is a joke, okay? In a real problem in reservoir simulation. So this just gives you a taste of how hard it might be actually to visualize. So yes, you probably wanted to punch your computer a couple of times. It's okay. I'm just exposing you to how a data. So now, these days, there's a lot of buzzwords calling big data. Okay? This is what big data is really about. It's data that we've always looked at. It's just there how do we process it on the computers that we have available? And that's a real time. Because we don't have trouble in sciences and engineering in general getting data these days. There's data everywhere. We have trouble processing it in real time. Okay? Or processing it, parsing through it as fast as we need to. And 3D type of visualization is one of the most involved processes in that sense. And you will, as engineers, you will often actually these days enter what they call caves, visualization caves, sort of a diagram that projects a reservoir all around you. And engineers kind of walk and possibly overlaps different type of data. Here, I didn't ask you to overlap anything. There was just one type of visualization. You were visualizing a surface of sand. Okay? But it could be a surface of different types of surfaces overlapping. Okay? Where is a fault? Where are the faults in the reservoir? Where are the valves? Where are the anything that where did the injection fluid go? And then you kind of this type of spatial visualization is important, but it might require a parallel computer in the background to actually power it. Okay? So just got exposed to a little of it. Now, that said, in terms of mechanics, we've seen a lot of you through the office hours, which is great. If you do in future when it gets involved like this, okay, we want you to come and help. We have tutors, we have office hours. Both Ligia and I are available, but there's also a bunch of tutors. So use the help. Talk to your classmates. Make sure to submit your work, but there's nothing wrong with discussing approaches in how to solve the problem. If it becomes obvious in this that you really can't deal with it and can't submit on time, there are two options. One is simply submit a little later. We typically take, for late homework, we typically take 10% off if it's within the same day. Okay? And even like within 24 hours. So please make sure that you actually finish it, even if it's a little later. It's still fine. It's better than not submit it at all. Do not give up. Second thing, when we do receive enough emails and enough people say, okay, we can't finish this on time, we postpone it. Okay? So we work in real time with this. Because sometimes it's not just this homework, but it might be 3 others. And we're open to it, but just honestly assess. Can you finish this? If you can finish it at a time, finish it and get it over with. But if there is a problem finishing it, please let us know and we'll act accordingly. Okay? It's not a big deal. What I don't want you to do is don't quit. Okay? Sometimes things will get difficult. There will be multiple assignments due. There will be some also possible issues in your private life. And, life happens. So just don't quit. Just keep going. Come back to it. Okay? Even if it's a little late, okay? It's okay. And emailing us and letting us know is typically the way to go. Okay? All right. And speaking of visualization, so on this website, we don't have this surface visualization that we know, but what we actually did is recorded a movie of going through the slices. So this is as I'm going through the stack, three-dimensional stack. This is how grains are changing in each cross section. This is one way to visualize. That three-dimensional surface that you did is prettier, right? And it gives a better spatial idea of how this works. Okay? Okay. So today, we're gonna very briefly wrap up our lecture on Python fundamentals. So what we were dealing with is reading data from a file, okay, and then reshaping it and using it. Okay? So for that, you often have to know what the data is. Okay? So here was a procedure that was opening that temperature file. Right? So just before that, there was my file opened. So this was the file we were looking at. So again, you have to know what the file is about and what's stored in it. If it's a text file that has some text at the beginning and then numbers, this is the procedure you're going to use. If it's just numbers, Okay, you can just read it in and immediately operate with numbers. So for instance, in homework, there was no text. There was just a bunch of numbers in the text file. It was a text file, but there was just numbers. Then when you read this in, the numbers, you can immediately operate with them. Do not use read line to read that first line. Okay? Because this read line that we were using in temperatures, here we open the data, and then we use this read line function. That's just simply to get this text at the beginning, mean, high, low, right? And get it out of the way. That's just for us humans to know what's in there. After that, we just need the numbers and operate with numbers. So if you use read line in a file that doesn't have any text that you want to get rid of, you're gonna compromise the data. Okay? You're gonna take out a bunch of numbers, right, and have an error, and not enough numbers when you then after that read the numbers. So be careful. Look at the file. Point is look at the file and decide what to do. And then once we have the numbers and reshape them, then it's relatively easy. But part of the example, both in the homework and here, was to figure out how do I reshape the data to make it into a usable form. And that can take quite a time. So give yourself time in general when you're analyzing data. All right. Now here we wanted to plot and see the averages, and visualization like this is important simply to see what the numbers are. Another suggested visualization in your homework was a histogram, which just looks at all of the numbers that you have and just plots their range and how many of each kind do you have. And you kind of decide how many bins. How many bins is up to you. You just want to have enough data points in one bin, so that you can actually see more general statistics about what it is that you're looking at. Okay, now at the very last end of last time, we also saved the data into a file. And again, we decide how to do that. Okay? In this case, we attempted to open a new file, and I called it temperature new, text file for writing. Okay? And then we wrote that first line in there. And then all of the numbers using an equivalent of that function from file. The problem in there when we opened that file, if you remember, there was everything was in one line, right? So there was no, it wasn't sort of formatted the same way that so we can go with, we need a for loop to do that effectively here, so I'm not gonna do that right now. But the computer is doing precisely what you're telling it to, so you have to be careful about how you format, but then you open, write something, and close. There is a more effective way to just in Python to just store numbers. And this is the one. I can use np functionality. And then all of the data that I read in, and it could be data on temperatures, it could be data that you read in from your homework, you can store in NumPy format, okay? But then you need Python to read it. No other software can read it. But the shape of the data and all of the details of the NumPy array will be saved, which if it's like three-dimensional array might be worthwhile. And in this case, I did not save any text or anything describing the data. You see the difference? So if it's just numbers, the most effective way to store an array is using this type of file. So NumPy save, and note that I need to do nothing else, just np.save. What is the name of the file? It's typically to put npy, so that we know that it's NumPy array, and whatever data you want to throw in there. That's it. No need to open, write something close. That's already built into this. But since there's no formatting other than saving that array, NumPy is taking care of that. And then if I want to read it from that file, I will just say np.load. So there's this save and load functionality that works really well if I'm just working with numerical data. Okay? So just numerical data, this is the most efficient way. But if I want any text, or if I want the file to be text kind of readable, I can open it as text and read as a human. These I can't read as a human. I gotta work through Python, okay? and load and save. So basically, those are the options that we often have, and there's multiple other options, but this gives you a taste of how do you get the data from somebody, use it, and then also store it in a way that other people can use. All right. So you can do this exercise on your own. You can actually, if you have any data right now open, you can quickly, that is NumPy array, you can quickly do this and load, and then see that you actually have the data. There's a number of others in these fundamentals. I'm just walking through the basics of input and output and how to interact with Python. There's a number of other very useful features. They're handling information. Pandas and dictionaries are the most common kind. It's sort of beyond introduction to numerical methods. If you take a data course or course on dealing with large data sets, these are going to be part of that course. And I have included some resources where you can actually take them and expand your knowledge. Okay? But they're very common for data analysis. All right. So as a recap of this fundamentals lecture, we're using Python because it's commonly accepted right now in industry, mostly for data analysis, and data could be in any branch of science and engineering. And basically, the mechanics of how we're using though is widely applicable. So we could be talking about any other programming environment. And I want you to think that way, because 10 years from now, maybe it won't be Python, maybe it will be something else that you will need to learn. It's a landscape that is constantly changing and evolving, and things are becoming better and faster as we go. Okay? Now, it does work on single computer. It actually works rather well in high-performance computing environments, in the sense that it's, even if it's not very fast on its own, it's very efficient in calling other faster programs. So I call actually Python a glue. It's also very close to the operating system. So in parallel computing environment, it can send data and move data around really efficiently. And that's typically the core problem when analyzing data. It's not the actual computational task that can be possibly lengthy, but it's relatively straightforward. It's like, how do I get all of the various inputs together? And that's where Python right now is a go-to language. So it could be faster in certain core tasks, but where it's not fast, it can call a faster programming language such as C and C++. All right. So a heavy-duty reservoir simulator is not necessarily written in Python or MATLAB or anything that we kind of introduce computing with. Okay? But it's nevertheless a very good way to get a taste of how it works, because we don't want you to look at the programming packages just as a black box. We want you to actually know how they function. All right. So without further ado, we're going to move on from fundamentals to basics of programming. That will enable us to be more efficient, and then we can actually start building some numerical methods that will actually solve problems. Okay. So first things first, we have already, let's say that we have imported a bunch of numbers. We need to be able to say something about those numbers. And more importantly, make a decision and act on it. And for that, I need to know how to compare things. If anything, in engineering, to make any decision, you gotta be able to figure out what is your baseline and how does a new case compare to that baseline. Otherwise, you can't make a decision. So in that sense, we need to introduce what's called relational operators. So if I have two numbers, I'd like to know which one is larger, which one is smaller, are they equal, are they different, and so forth. So let's play with that. For that, we need a type called, so I'm going to go to my browser, I'm going to find, and by the way, this third lecture is uploaded, including its Python scripts that I'm going to use. It's already on Canvas. So I'm going to do File, New Notebook.
And I'm going to call this Lecture 3.1 Relational. I'm just going to call it 3.1. All right. So let's say that my A is 2 and B is 5. And I can compare them the way you would expect, larger than, smaller than. So I'm saying print A larger than B. So this is almost a question. A larger than B is technically either true or not true, and we call that Boolean type or logical type. So there is a type that is true or false. Sometimes that's 1 and 0, true or false, right? But here it evaluates, it's called a logical or Boolean type, and this evaluates as false because 2 is not larger than 5, okay? And if I print B larger than A, or let's follow the same sequence, A less than B, that's true, and it is true. I can keep going. I can also ask, hey, are they equal? And that's not true. And the way I ask, are they different? I would print A exclamation point equals to B. And that indeed is true. Why it is that I have to put 2 equal signs here? So if I just had 1, what would happen? So equals to, and we've used it so far, sets something to a value. It's assignment rather than questioning whether something is true. So we said, okay, let's throw in 2. Okay. So this equal is actually asking, hey, are they equal, rather than assigning. Because if I said A is equal to B, my answers would change. Because now I have actually assigned value of B to A. So now my A is 5. And no, neither of them is larger, false, false. They are actually equal because I set one to the other. They're not different. You see how examples have changed? So watch out, this is single equal assigns value. Equal asks whether they are equal. It's an important distinction, and because our brains kind of like works both ways, single equal works both ways in our brain, it's a common way to introduce a mistake in your program and overwrite some data too. So be careful about that. Did everybody get a chance to try this out? So again, we call these relational or comparison operators. And this is sort of a list of all of them that you can use. There's larger than, less than, equal to, equals to, not equal to, greater than or equal, less than or equal. So those are the most common ones. And they need 2 things to compare. Now we can also combine them. And we combine different things with and or not. I could negate one thing. So not true is false, right? So let's see how to combine them. So introduce yourself as C is equal to 10, and then see, hey, is A less than B? What is A less than B or B less than C? Let me do it with you. I'm going into a new one. So my C is equal to 10. A less than B or B less than C. And I'm going to print them individually as well, just to break it down. So I have A less than B, B less than C, and then this OR business. So both of these are true. Then true or true is also true. Let's make one of them false. So let's say B larger than C. B is 5, by the way. So 5 is not larger than 10. So this is false, but then I have true or false evaluates to true. So as long as one of these statements is true, and I have or, logically, just like when you're thinking about it, it's going to be true. What happens with and? Let's try print A less than B and B larger than C. So now when I have true and false, that evaluates to false. So both of them have to be true for that to evaluate to true. And I say and, sort of logically and also in language. My joke about and operator is that my parents worked with an and operator. So the way it would affect me as a child, I'd come to my dad and, Dad, can you go to the movies? Of course you can. Then I come back home from school, Dad, can you give me money for movies? Your mother wants to speak to you. So I go to my mom says no, and the answer is then no. Yes and no. My parents always evaluated to no. They made their life much simpler that way. I can appreciate it now. I did not appreciate it as a child. They were strict. Very loving, but strict. Again, I appreciate it now. There are certain things I didn't appreciate as a child because of that. So they were and. They operated using and. That's a more stricter way to operate in parenting or engineering. Okay? Okay. So now I have actually tools to build things, right? And why do we need this? I pour in a bunch of data. I have to figure out, well, is anybody above certain threshold, right? Do I have, out of the porosities that I measure in my reservoir, is there any above 30%? If yes, count yourself lucky. Okay? So things like those. So my decisions might depend on kind of scoping the data and figuring out what is true, what is not. So now I need to actually a tool to make that decision in terms of programming. So the tool we use is if statement, first of the tools. Okay? So basically the way we will build the decision or redirect my program based on what data tells me is by asking if something is true, then do this. Otherwise, do this. So we're going to get to the otherwise part, which is here, else. Okay. But let's try this out. If a less than 0, I could, for instance, in the simplest of the cases, print a is negative. Let's give that a shot. Now, before we type that in, I want you to pay attention to syntax. How does Python really know that I'm telling it what to do? So there is important part here is column, okay? And then I also have to indent. And maybe I want to just print one thing. Maybe I want more things to happen, which takes some coding. All of those, that block of statements would be indented, and that's how Python knows that that's what it should do after this is true. Okay? So let's try. So again, syntax is important because details here matter. So let's say if a is larger than 0, and you can see when you press enter, it's going to indent on its own. Well, then leave it be, don't mess with it. So when I evaluate it, nothing happens. Is everything okay with my code?
Yes.
Because A is positive. Let's change A to something negative to test this. So I'm setting A to -1 just before the statement. Aha, okay. Did everybody get a chance to do? Now, if I don't indent something, or I'm going to print something else that has nothing to do with A. What will happen now? So hello will print no matter what. Because it's effectively after each statement. So indenting is important. So in this case, yes, it prints, but even if it's positive, hello still prints. Because effectively, it's not part of each statement. It's a code after. Yes?
So you don't need the semicolon at the end?
Semicolon is needed.
Oh, it is.
Yes, it is.
Not the colon.
A column. Oh, here?
Yeah.
No.
Okay.
Kind of Python could care less about semicolons. But semicolons exist in a lot of languages, so it just decided to have them and ignore them. What I appreciate in MATLAB, if you put semicolon, then nothing will print out to the screen, which is kind of useful. Otherwise, it executes all the same, but in one case it prints the result and in the other one it doesn't, which I find useful. But here, Python kind of just actively ignores semicolons. And again, a lot of programmers have transferred from other languages, and in C you have to have a semicolon. Okay. Now, I would like to do also something. If A is not negative or whatever, I want to have if statement, but I would like some other cases, and I'm going to show you the structure first. Okay. So basically, if the statement is true, I'm going to execute a bunch of commands, and that's going to be the end. if the statement is false, nothing will happen if I just have one if statement. However, I could actually now branch out in my decision making. So I could have, hey, if statement is true, I execute a bunch of commands. And I'm done then. If not, I could then go to another statement and see whether it's true and execute something. And if not, execute something else. And frankly, I could keep going. It would be a code that is hard to read, but it would work. Okay? So basically, I could have if some expression, and then there's a block of statements that belongs to it. Else if, which is short elif, else if. I have another expression, and then a block of statements that matches it. Else if, which is elif, another statement. I could keep going like that. Okay? And there could be actually an else at the very end that kind of catches it all. If nothing above is true, I can catch it. But let's try this one. So let's try first without coding. If I have x that is -4 and y is -3. If I go into the first block, is -4 larger than -3? Is that true or false? That's false. Will I execute this line? No, right? Because -4 larger than -3 is false, so I'm not going to do anything in this first block. I'm going to go to the next one. -4 divided by -3 is 4/3. Is that larger than 0? That's true. So I'm going to set C to be logarithm value of that. We might need to do np.load there. Import NumPy. Yeah. And then I could do this. I could actually keep going. So let's give it a try. I don't even know what I had on slides. I just came up with some C. Okay. And then I was asking if y over x and it's a very good programming practice to, when none of the above actually took place, it's good to have sort of a catch-all warning. Neither x larger than y nor y over x. And I'm going to print C no matter what. So let's go through this a little. So in this case, we said if it's -4 divided by, in this first case, okay, then this should basically execute. So let's see whether C is approximately sounds about right. Now let's play with this a little. And also see so there is one vulnerability in the code that I wrote down. If this happens, C is something. If this happens, C is something. Otherwise, I don't set C. I print a warning, which is good, first step, but I don't set C. Now, I'm just telling you what to do, and you're like, so what? Yeah, I can do that. But in real world, you will often put together a piece of code that you thought was good, right? But it might be that you didn't test all of the cases and you didn't catch the fact that you might have C not set. And the rest of the code depends on that C, whatever the C does. Right? So this is part of the code testing. Okay? And you have to be attuned to it. So whenever you write a piece of code, you got to kind of test a couple of examples, and not just one, okay? But different. So let's test it with different X's and Y's. What if I have this case? So I need to also clear all. So here, I actually set it. Here, another thing happened. I had C in memory, so it printed my old C, because I set it on the previous execution. So I got that value set on the previous execution, but it gave me a warning. By the way, none of the above was true. You didn't really change the value of C. But if I didn't execute this once, so if I stopped and restarted, speaking of, whenever you are in trouble or something's not working, you can actually stop the kernel here and clear output. So when I clear the output, C shouldn't exist anymore. So let's try to execute this cell. Name C is not defined because I never said. Is everybody catching the little details? So these are important because this is what bugs you the most when you're solving your homework. You kind of forget what you did, or you erase it, you come back, oh, it worked before, now it doesn't work, that type of a thing. That's because you had these small things sprinkled in the code. Again, remember, computer is doing precisely what you told it, and not more. But there could be things hanging in memory from before, and sometimes it's going to execute because it has things hanging in the memory from before. That doesn't make it right. That just makes it not complaining. Okay? So good programming practice is to try to set things. Well, if I set the C as a sort of a default value to 0, or maybe in this else statement, I can set it to 0. That's another option. Then at least it's going to be set, and hopefully that avoids some of the errors. Here we don't have an exact application where that's crucial for something, but it could be. Why is it crucial? Let's say that the C variable was something. So we had a test at 10 minutes before the class, they had the testing for the siren, right? So let's say that that testing or that sound effect depended on this C. It wouldn't execute. Okay? The warning or whatever was supposed to roll out would not execute because you did not set one variable in there. Okay? Is that important? Well, if warnings don't execute, that can cause safety concerns, okay? So again, it could be important. So I call that defensive programming. You kind of like put things in there for safety checks. Statements like this are good. comments of what are things doing are good, and making sure that variables are set. All right. So now we know how to do decision making and acting based on whatever data is telling me. I want you to do a quick exercise. Input the number from keyboard. Remember that function input. And determine whether the number is even or odd. And inform yourself or user of your little piece of code whether that number is even or odd. So print something on the screen. So your first task is to figure out how to input something. And then your mathematical task is how do I decide if the number is even or odd? And that might need figuring out, there's a function in math that you used. So you might need to figure out how Python does it. And needless to say, this is going to be your little quiz. So we can walk around and help out with some positions.